So on this one, we're going to try to develop a 90% confidence interval. Now, a 90% confidence interval means we are estimating, but estimating such that there's a 10% degree of uncertainty to our estimate. There's always going to be some uncertainty. It's impossible to be 100% sure when we're taking an estimate, unless if we're 100% sure it's not an estimate, right? It's something we know for certain. So, for example, when you guess your grade, you might say, I think I have a C plus, or I think I have a B, and you say maybe plus or minus 5 points. So if you say you have a B, maybe you're saying I have an 85 plus or minus 5, which means you have anywhere from an 80 up through somewhere from an 80 up through a 90 plus or minus 5, because that's the B range, right? And that's what an interval estimate is kind of doing. Based on our sample mean, we're trying to get an estimate of the population mean. So how do we go about doing that for a 90%? Okay, just like we did with 95%, the first thing we have to do is we have to figure out what z-value, what z-score would cut off 90% of the area under the curve symmetrically. So I need to find z of alpha over 2, where alpha is my percent uncertainty, my chance of that this interval does not contain the mean. So it's going to be z of 0.1 over 2, which is z of 0.05. And if you type that in, you get 1.6, like 449 or something like that. And we'll just call that 1.645. So that is my z-score. So let me put that on here. It's about right there, and it's about like right there, maybe a little further. And inside, here's the mean. Inside is 90% of the population, 45% on both sides. Okay, so if you are a X bar, there is a 90% chance that you are in this green striped area. You're somewhere in there. 90% chance. Does that mean you're definitely in there? No, not definitely. There is a chance that you could be outside. What percent chance is there? There's a 10% chance that you might be out here. So when we take a sample, that sample could be anywhere on this bell curve. But because most of the X bars are in here, 90% of them, there's a small chance that the X bar that we actually found might end up out there. And so then I can use what I call and I just came up with this, the arm's length rule. And the arm's length principle says that if you're an arm's length of me, I'm an arm's length of you, if our arms are the same size. And so if I'm you and you're X bar, if my arms are stretched out so that I touch 90% of the X bars, there's a 90% I'm touching you, and there's a 90% chance if you stretch out your arms the same distance that you're touching me. Let's say here's X bar. I'm going to put X bar inside the green because that's likely where it's at. So here's X bar. Let's say it's right here. Okay? If I put an arrow on there equal to the arrow you see above, you see how I would touch X bar. You can see if I'm over here on this side and I stretch that arm out, I would touch X bar. Yes, I have an arm going in the other direction, but I still touch X bar. The only place I do not touch X bar is if I'm out here and I put that arrow on there, same length arrow, it doesn't reach. Okay? But that only happens 10% of the time. For a randomly sampled sample mean, that's kind of rare. So now that we understand that, hopefully you get that. How do we actually find it? Well, it's very simple. Now that we know it's 1.65, the actual length of this arm here is 1.645 standard errors. So all we have to do is figure out the standard errors and add that to either side of x bar, and we will get an interval for any x bar we have that has a 90% chance of capturing the mean, of containing the mean somewhere in there. So let's do it. I'm going to go here, and I'm going to put in my sample mean, which was 103. Next, I hit the plus or minus button, and then I hit my z alpha over 2. Now, alpha over 2, alpha was 0.10 divided by 2. Okay, and we actually already got that as 1.065, but I'm going to show you how to enter it all at once. Now I'm going to multiply that by the standard error. The standard error is the standard deviation of the population, which was known, divided by the square root of the sample size, which is 50. And I hit enter, and it gives me my upper and lower bounds. So there's a 90% chance that the mean is between these two numbers. The two numbers are 101.67. I have to go to 3 decimal places, 0.671. So 101.671 and 104.3290. So we'll leave it 101.3 or 104.329. And that's it. Hopefully it didn't log me out. What did I do wrong? 103. Let's try it one more time. Calculator. I hate when I get it wrong, but it happens. Okay. Mean 103. Maybe I typed something in wrong. Plus or minus. I want a 90%, right? 90% confidence interval. So let me just type in 0.05 in there. And we're multiplying that by, not that, but we're multiplying z by the standard error, which is sigma 13 divided by the square root of the sample size, which is 50. Enter. Oh yeah, it was way off. I don't know what I hit last time, but let's clear those. Let's clear that one. So it's 99.9759, so 99.976 is that one. And one more try. 106.024. 106.024. Okay. And that's that. So I hope you get the arm's length principle. I should have time for one more because I can do these pretty quickly. So let me see. Let's do another practice. A laboratory in New York is interested in finding the mean chloride level for a healthy resident in the state. A random sample of 80 healthy residents has a mean chloride level of 102 I don't know what those are. Yeah, whatever that is. Okay. If it is known that the chloride levels in healthy individuals residing in New York have a standard deviation of 41 MEQs per liter, whatever that is, find a 95% confidence interval. So we know 95% is a z of 1.96 from the other video, but even if we didn't, we know that because there's 80 and because the standard deviation of the population is known to be 41, we're going to use a z. Sample size is bigger than 30, and the standard deviation for the population sigma is known. So here we go. I'm going to type it all in. I start with the mean chloride level is 102. That's the sample mean. It's 102. I hit the plus or minus button, so it'll calculate both for me at once. And then I need z of alpha over 2. Alpha over 2 is 0.05 divided by 2, which is 0.025. So you can just type that in. Arrow out of that times how many, what's my standard deviation? 41. Whoops, that's 14. 41 divided by the square root of 80, which is about 9. And there is our interval. So lower limit 93.0156 is 93.016. And the upper limit is 110.984. And we have a 95% chance that the mean is actually in there. Okay, that's it. I hope that was helpful. Bye-bye. Oh, it's so long.